everyone, welcome back to Project Pro YouTube channel. This is me Simran Anand, and in this video I'm going to discuss the second part of natural language processing tutorial. In our previous video, which was the part 1 of the NLP tutorial, I had discussed about the various NLP techniques and methods that you should be aware of for natural language processing, some of the real life use cases, and also the methods that you can implement for natural language processing using NLTK, which is Natural Language Toolkit. So coming to our plan, which I also discussed in the previous video, that the part 2 will delve into model development. So in this video, I'm going to discuss about ML model development to classify text using natural language processing. In our previous video, I had taken a data set, if you remember, which was movie reviews data set. It's a textual data set consisting of 2000 rows. So there were 2000 features. So in that we had to build a model to actually classify the movies into positive, the sentiment of the movies into positive and negative. So in this video, I'm going to be explaining you how you can actually implement different supervised as well as supervised and unsupervised machine learning techniques and algorithms to build models, how to evaluate ML models effectively to classify text, and the classification will be binary classification for this demonstration of this video. Then I'm going to also explain you similarity concepts. So let's begin. If you see the brief overview, we had implemented in the previous video, I had demonstrated till here where I was explaining you, we got the most common words. So once we get the most common words after all the natural language processing techniques were applied, like the techniques which were covered were tokenization, stemming, lemmatization, parts of speech tagging, and the normal cleaning of the data. Once after you have applied all the text pre-processing techniques, of course, the next model should be, in order to classify, you need to actually apply ML algorithms. Now see, ML algorithms can only be applied once word embedding, something called as vectorization, is performed on the text, because a model can only understand zeros and ones, as we all know it. So we need to actually encode the text into a format which the model can understand, and that format is going to be a sparse matrix. It's going to be a sparse matrix, and when I say sparse matrix, it's containing negligible or zero values. Mostly the values are zero in it. So once we encode the words which are present in the reviews, the movie reviews data set consists of words which are, or sentences which are reviews. So we are going to encode them into vectors. So we can now to actually vectorize them. When I say vectorize, over here, if you see, there are actually more than 710,000 unique words in the data set, of course, and on top of that, top 15 most were the common words. But out of that, we need some fraction, a sizable fraction of the unique words in our vocabulary in order and find out if each of these words occurs in a review. So for getting that particular fraction, I have taken that as 1500. And we are going to use those 1500 as the features. So these 1500 most common words are going to be taken as the features to actually train our model on classification tasks. So I've taken that in this code, and Y is going to be our label. So we have a label data set. So we are not of course, we know that supervised learning works on label data set. So we're going to also test our program on all the famous supervised machine learning algorithms for classification tasks, as well as I would also be using K-means clustering, which is actually unsupervised learning, and actually we're going to evaluate which machine learning model is going to give us a better performance. So once that you have actually learned about all the, I'm assuming that you all must have heard about different supervised and unsupervised techniques. Out of them, what we're going to use over here for today's agenda is that we're going to use K nearest neighbor to test on decision tree, random forest, logistic regression, SGD, which is stochastic gradient descent classifier, and support vector machine. We're going to use this, and the main purpose, we know something called a concept like hyperparameter tuning. In my previous videos, I was talking about concept of hyperparameter tuning, where you actually, it is like ideal parameters which have to be taken into consideration for building the models for getting better evaluation results. So there are different hyperparameter tuning techniques like randomized search, grid search, cross-validated grid search CV. So in this case, we are going to use and we're going to use the sklearn library or the package in Python, by the way, for model building. And all these classifiers like KNN, decision tree are all being imported from the sklearn library in Python. And then from model selection submodule of sklearn, we are importing randomized search CV and grid search CV. So I'm going to take into consideration cross-validated grid search for actually tuning in the hyperparameters and also getting the best hyperparameters from the search space and then building the models testing it on the test data on top of that. So let's, if you see this classifiers is a list of all the 6 machine learning algorithms which we are going to test upon, and we are going to make a dictionary over here. So this is a params dic, which is a list of dictionaries. Each element is a dictionary consisting of, so say for the KNN neighborhood, which is K nearest neighborhood. For the KNN classifier, we need parameters like n neighbors. So the number of neighbors are 5, 10. We are starting from 5, 5, 10, 25, 35, 50. So out of all these, which one is the best hyperparameter, which is the best or the ideal n neighbor? The number of neighbor, which will actually give us a better result, will be taken by the model. That is going to be taken care of by grid search CV method. So we are similarly for decision tree classifier, we have something called as max depth parameter, and I'm assigning random values like 5, 10, 15. So in this search space, whichever is going to give us the best performance is going to be taken into consideration. Next, similarly for random forest, we have n estimators. For more information about how these, what are the parameters of all these model classifiers and all, you can definitely head over to the sklearn documentation, because all this is about scikit-learn. So you can go to the scikit-learn documentation to give it'll elaborate on the parameters, what they stand for, and about the machine learning algorithms. But to put into brief, the main agenda over here is to classify text, to classify whether the text is positive or negative, and to test in evaluate which model is going to perform better in terms of the accuracy. That is the main goal of this video, the part of the video which I'm going to demonstrate. So if you see this next parameter over here for the logistic regression, we have C penalty, which is L2 regularization. So I in my previous videos, I had talked about what is regularization. So that is, these are hyperparameters basically to avoid overfitting problems and so on. Max iteration. Similarly for SGD classifier, that is stochastic gradient descent, I have set the max iter, and kernel for SVC. So we have support vector machine. For that we have different kernels, like the default being linear kernel, which of course it gives better performance as well in most cases. So we're going to also test which kernels will give us a better accuracy. We have taken different kernels like linear, sigmoid, polykernel, and also RBF, which is radial basis function kernel. Now coming to, I've done the train test split here. So train test split is basically for dividing your entire data set into training and test data set. So when you're dividing the trained data set, firstly the X, which is the feature, has been already vectorized. If you see the above code I was demonstrating, you have converted that into a sparse matrix already. This is the featureization code, by the way. To find the features, I have the X vector of ours, basically the X which was in the part of the data frame. We have something called as X and Y, which is target label, and the feature label. So we are actually vectorizing the feature label, encoding into a format. Like this is the vector. If you do feature vector.shape, this is the format. So it has 2000 rows and 1500 columns. And columns over here are going to be the features, which are the words which you are going to train your models upon. Since we have taken a fraction of the words, which is 1500, for training the model on. Now coming to this train test split, so I have divided that. Feature vector Y are taken as parameters. Test size is 0.2 because we are taking 80% for training and 20% for testing. Random state is 42. Now random state over here, the default is none, but you have to set it to a particular value. It can be either 0, 42. These can be taken as a hyperparameter, because each time, if you do not set a random state, each time when you actually train your model, it will give us a different train and test data set. So in order to avoid that, you're actually setting this random state to a particular value, so that it gives us the same kind of division of the data set and the same result every time. So we are applying grid search CV over here, which is cross validation grid search on the model and the to get the best hyperparameters. Then we are fitting our classifier on the trained data set and predicted on the test data set. After you do this, you're going to get the best parameters, and along with that also the accuracy. So when you check over here the best parameters, you will see that KNN is giving us an accuracy of 0.6 and decision tree 0.63, but random forest is given 0.79, logistic is 0.8, SGD as 0.8, and SVM also 0.8. So from here we can conclude that which one is the best model performing for our data set. We can see that the highest is given by logistic regression here, followed by stochastic gradient descent and support vector machine. So these three models are performing best for our binary classification of text data. and the text data is a movie reviews data. That was something we understood about the model development. Now, these are all the supervised techniques. What I've explained you is the supervised techniques, which is giving us a fairly good accuracy. But when because we have a labeled data set, but now we're going to check it on clustering. Now, clustering is k-means clustering. I'm going to explain you on, and that is a unsupervised learning, machine learning. So we're going to check how our model is going to actually perform on that. But before delving into that, there is a concept of text similarity and clustering. Now, both of these are unsupervised techniques, I would say. See, now since we have positive and negative as two classes of binary classification for our as a label, so because our labeled column has only 1 and 0, which is positive and negative. So we have to create two clusters in order to cluster our data. Now, the main concept of cluster I would put into short for you. If you have not heard of that, cluster is basically for similar data points, grouping similar data points together such that the data points of the same cluster have most similarity. The similarity is going to be maximized, and the data points between two different clusters are going to be very dissimilar in nature. That is the concept of clustering. Of course, there are different types of clustering like hierarchical clustering and so on. But in this particular video, I'm going to demonstrate k-means clustering, and that's unsupervised technique. So on doing this particular k-means clustering, there is a concept of TF-IDF vectorizer, and that is required over here because since we are do not need the information about the presence or absence of words, but also we need the number of times the words are occurring. That is the frequency or the occurrences of the word. So since we have to deal something with the frequency of the words in each document as well, not only in the word in each row, but also in the documents. Each row of the data frame can be considered as a document. So we are going to take that into consideration. So that is why we are making use of TF-IDF, which stands for term frequency inverse document frequency technique to look at the frequency distribution. So this is the code for k-means, where I'm again using sklearn library over here. And delving further, from feature extraction of the text library, I'm importing TF-IDF vectorizer, and I'm passing in two parameters, max df. Df stands for document frequency. These two are set by us. So max df is like the upper ceiling value, min df is like the low cutoff value. So only those words, it may be that in the entire corpus of text there are highly repetitive words like the and so on, which can be considered as stop words, and they do not add significant information to the data. As I was explaining in the previous video, which is the part 1 of the tutorial, I was explaining of stop words removal and what exactly is stop words. So in order to remove the stop words which are highly frequently occurring, I've set that particular value is 0.8, such that the words which are occurring more than 80% of time in all the documents, or in more than 80% of the documents, or in our case documents is the rows, more than 80% of the rows, those have to be eliminated as stop words. So that is why I'm setting the parameter over here to TF-IDF vectorizer, and min df as 0.1. That is the more rare words. So the rare words which are occurring less than 10% time, that has to be again eliminated. Only the words having frequency between 10% and 80% have to be kept and vectorized by TF-IDF vectorizer. That was, I hope I have made this concept of parameter passing to TF-IDF vectorizer clear to you. Then we are fitting in the vectorizer. We have the TF-IDF vectorizer, assign it to a label vectorizer. I'm fitting in the data we have, that is each row or each record of the text column of data frame. On doing that, then transforming it. So as you know, the concept of fit transform, now transforming it into a sparse matrix of zeros, such that each value in the sparse matrix will not only indicate whether the word is present or not, but also the frequency of the word present or not. After doing that, we get TF-IDF vec.shape. So we have 2000 rows and 431 columns right now. So that was the result of after performing the vectorization. Then I'm going to fit the k-means clustering, apply the k-means clustering algorithm over here, passing in the number of clusters as 2. Then n init, the value is set over here as 20, and n init over here is the number of times the initialization of centroids has to be done. In k-means, the centroid will keep updating itself. Centroid is the center point of the cluster. That it has to be it has to initialize itself each time of the run. So the number of times it has to be initialized, the centroid is going to change, is 20 over here. The default is 10. So random state again I've set to 42, and then fit the model on the KNN model again on the trained data. On performing the training, I will see that on the test data set, which is Y, on the train and the test accuracy, on the train, which is Y train, and Y test, which is the test data, I'll see that it's found that the accuracy is just around 50. You can see the accuracy over here, the train being that 53.8%, test being 51.5%, which of course is not not a proper, indicative, or we can say it's not giving us good results in comparison to the previous supervised techniques I was applying. So we can conclude saying that, instead of going with unsupervised techniques like K-means clustering, supervised learning, which were decision trees, logistic regression, SVM, SGD classifiers, worked better, and they gave better word representations for our model. That was all about model building, evaluating the models and so on. Coming to the very interesting topic of text similarity. Now see, text similarity is gaining momentum these days because there are various real life use cases also where you actually want to compare text. Some of the cases I would say, now see, when I say compare two texts into matching two texts, if you have two texts and you're going to actually give the similarity score as to how similar the two texts are, in what way are they similar? Are you comparing the word length, or the way, converting the two words you have into vectors and then comparing them based on the lengths of the two vectors or the distance between the two vectors in the vector search space? Or are you going to compare their meaning of the two words? Or is it because you're just comparing word by word and character by character? Some texts are just not conveying any meaning, but they just because they have a word by word comparison. If you do, the words are very close by matching. So in such cases, the similarity score will be higher. So in that, in that way, I could say that text similarity is also having different types. Coming to the types of similarity, text similarity, there are different types like semantic similarity, lexical similarity, cosine similarity, Levestein distance, Jacobian base, contextual similarity, and so on. But to give you a brief about it, as the word says here, semantic similarity. Now, the Spacey model has, Spacey, if you know, it's a library like NLTK, Spacey has its own semantic similarity. So you can actually perform semantic similarity using Spacey. And the main purpose of semantic similarity is to actually compare, find the similarity between two texts based on taking the meaning of the two texts into consideration. So that is, as I've told, semantic refers to meaning. So it's going to check the meaning of the word. Lexical, on the other hand, lexical similarity is going to check word by word. As you know, lexicon is dictionary, so it's word by word. So when you say lexical similarity of two sentences, like one sentence is the brown fox jumped, and the second sentence is jumped the brown fox. Both of them are having the same combination of words. The words are same, but then the arrangement is different. So when I apply the lexical similarity between them, I'm going to get a very high score. But had I applied the semantic similarity between two such, I'm going to get a almost a very not a good score, because it's going to compare the meaning. All the meaning is going to be different. The sentence I've told is one example, but there are many different cases where you actually you want the semantic similarity, you want to actually give emphasis on the meaning, so the meaning is preserved in the two texts, and you want to compare two texts, how close by in the meaning they are. Then I recommend to go with semantic similarity. On the other hand, you want to do word by word comparison or character based comparison, you can go with lexical similarity. Cosine similarity is when you have two word vectors, you're going to find the distance between them. Now distance between them is that the more closer the distance, or more nearer the words, the more closer in meaning they are, is what is inferred in cosine similarity. So this was all just about cosine similarity, lexical, semantic similarity. Now see, cosine similarity, you can do it by different metrics. You can find the, when I said distance between them, distance, the cosine similarity, as you know, it finds the cosine of the angle between the two vectors. And to find the distance, there are different other metrics as well, like Levestein distance. You can also find the Jacobian distance, the distance like Manhattan distance, Euclidean distance, and so on. But now coming to another metric which is interesting, which is Jacobian base. Now Jacobian base is a similar, a text similarity. The way it does is that it is something considered like intersection over union, where the overlapping nature of the two words is going to be emphasized on. So it's something like the intersection between the two words divided by the union between them. That is the formula of Jacobian base similarity. Now that was all, to give you a gist about how you can actually convert words into vectors and then find the similarity between them. Similarity can be considered in the form of keywords. Now when I say keywords, say you have someone's resume, and then for resume parsing, you need to extract and give importance to the keywords. Now when I'm saying word by word comparison, that is where lexical similarity comes into picture. But on the other hand, if you want just the meaning of the words, suppose if it's a paraphrased content and you want to see the meaning, the way in which two words are actually matching, or how similar two sentences or words are, then semantic similarity comes into picture. And those are the real life applications of text similarity. So in word embedding as well, in this particular demo of the code which I'm explaining you, we'll also look into how we can actually make use of Gensim as well as NLTK. Also, I'm going to explain you how the difference between using pre-trained models as well as model trained from scratch, and which is giving a better performance. So nowadays we've heard of a lot of pre-trained models giving state of art architectures and all, and we are actually fine tuning the pre-trained models. We're using pre-trained model, pruning it, and using a fine tuning the pre-trained model, and it's giving better results as well, because already it's trained on a massive amount of data that performs better. We could also look into how they are performing better, what are the results they are giving, and also explain you the different text similarity measures and the results of them. So if you see here, word embedding is nothing but this vector representation of words. As I've told you in the previous, while demonstrating the codes as well, you're converting words into vectors. That is nothing but the concept of word vectorization of words from the vocabulary that considers the context of the word. Now, when you're actually doing word embedding, the different, word embedding approaches in NLP, to name a few, they are word-to-vec model, GLOVE model. GLOVE stands for global vector representations for words. Then you have fast text model that you can look into. Another word embedding model can be, count vectorizer model. Even TF-IDF vectorizer is a simple, word vectorization, I would say. Even like word2vec, which I'm going to demonstrate over here from Gensim model, is going to give us results, pretty good results only. So in such ways, there are different models. Even NSkipgram model is another model, word embedding model. Now, different word embedding models, what they differ in is that, and BERT as well. BERT is, especially a very good model, giving us better results, because it also not only gives us the context of it looks into the context of the neighboring words as well, and also some of the out of vocabulary words also handled by in such cases, because some of the word embedding techniques, they actually are not able to handle the out of vocabulary words, or the words which are not, it has not seen ever. So such models fail on out of vocabulary words, but on the other hand, BERT is now overcomes that problem, so that is preferred, and also it takes into consideration the neighboring words, the context of the word is preserved. So all these can be, word, when you're embedding a model, word embedding, you're embedding words, it can consider the context of the word, model the semantic reasoning. Now, when I say semantic reasoning, the meaning between the vectors of the word, and so on. So also the focus word, along with that, the neighboring words. So when I say word-to-vec model, it simply models words which are one-hot encoded along with the neighboring words to capture the context and relative importance of the different words. So I'm importing Gensim over here, which is generate similarity. This is the short form is Gensim. So from nltk.corpus, import Brown. Brown is the data set which I'm going to import from NLTK. I'm downloading that dataset, Brown dataset, and training the model from scratch. This is not a pre-trained model. I'm going to train the word-to-vec model using the Brown dataset from LTK, and then apply word-to-vec word embedding model from Gensim to see how the results are. So after I do that, apply the word-to-vec model, and name it Brown.embedding. Then we will see that university.shape. You see here that it has represented this particular word university in its vocabulary as a 100-dimensional vector. So this particular word is going to be vectorized into some dimension, and the dimension is 100-dimensional. And if you see the similarity, so if I word vector, so wv dot similarity is the method from Gensim. I'm going to compare or find the similarity score between these two words, university and school. You see here 0.81 is the around 0.815 is the similarity score. But if you see, similarity score between university and college is 0.92. So we have a higher similarity score between university and college than university and school. That was all about how similarity is also working with word embedding model here. Now coming to this next one, which is using the pre-trained model from NLTK. I've used the pre-trained model over here from trained on the Google News data set of NLTK, and then fitted that model, using a prune version of that, fitted the model and checking what kind of results we are getting. So if I see over here, I've got here around, the words represented as 300-dimensional vectors, and there are nearly, you can see, 43,981. So nearly 44,000 unique words in the model's vocabulary. And when I find the similarity, the most similar, and I give the top end value as 3 here. So the topmost three words which are highly similar to this queen word are going to be retrieved by the model. So when I see here, queens is assigned the value of 0.73 queens, but I'm passing in queen over here. So queens is given 0.73, princess and king with their similarity scores. I can see the top three most similar words being retrieved. Similarly, if I do most similar, positive equal to women, king, negative equal to man. So I'm categorizing man to negative class, positive class, women and king. And the most top n value over here is set to 1. So top n is the, the topmost ranking words in terms of similarity are going to be retrieved by the model. So when I pass in 1, the topmost most similar word is going to be retrieved. So similar to that, women is queen over here with the similarity score of 0.7. So that was all about how similarity measures are going to be retrieved. So as we can see here, words like queen, it can give a ranking of words most similar to it, words that are close to the vector of queen, and also list out words that are opposite like king. King is actually dynamically, diametrically opposite to queen. So this performance was not seen in the previous case where we were training the model. But when we use the pre-trained model, this is possible. We are actually getting word vectorizations very similar to the words and also opposite in nature. So that was the key advantage of using pre-trained models, which in our case was, the Google News dataset trained upon. That was all about the second video. The third video, do not miss out on the third video, because the third video is actually going to talk about another real life application of NLP, which is very interesting. That is question answer system. You learn about how to build extractive question answering system and next word prediction using NLP, and then deploying the same using fast API. I'm going to make you build a machine learning pipeline using Hugging Face transformers, and then deploy this particular system using fast API, which is a web framework very prominent these days. Then you can later dockerize it and build into websites and apps.